Hey, hello everyone. How was your recess week? Good? Feels like quite a long time, haven't seen many of you. So let's hope you still remember what we did, what we learned. And also the individual project, we extend the deadline for another 3 days actually, so to give you a little bit extra time to examine what you have done. Since I feel like many students have completed already, while some have not started, so it's a warning sign there. Just use this last week to prepare well for your project. Okay, so last time we paused at the linear programming part. So we started to see how we solve those LP problems through several different approaches. So first one, the question here, I remember we did interesting practice last year. It's like if you to count how many number of extreme points will there be based on some of the questions we give you, like the constraints. We have 3 constraints. If you have n constraints, how many extreme points will there be? So it's just, you can imagine about the number. What's an extreme point? It's kind of a huge number, but if you can give exact representative, but anyway, that just give you a sense where if you want to solve in a naive way to search all the possible extreme points, that's very computational expensive. That's how we need the algorithms. So for optimization algorithms, it is to use the certain search methods, like either the 2 typical ones introduced, interior point method, where we search from a center point and then go to find the improvements. Or we use the simplex method to search the boundary conditions and found the nodes. So that's algorithms for LP. We will have a look later. But first we define, so last time we stopped here, we defined the standard form of linear programming. Why do we need standard form? You can write your problem in any way, but when you try to use some standard algorithm to solve it, it's kind of like a protocol. You need to write in a standard form. Therefore, those solving strategies are applicable to your problem. So here we define this LP in standard form if it has only equality non-constraints and have only non-negative variables. So of course, all optimization problems, it's always with those inequalities for constraints and with some of the variables that can be larger or can be negative. So those things are from the natural formulation. But when we solve it, we define the standard form with this type of problem formulation. We turn all the inequalities to equalities. How do we do that? So that's the first trick. How do we turn an inequality to an equation, to an equality? And why do we need to do that? So this is the first thing we know, because we always learn from solving equations. From kindergarten, we learn how to solve those equations from basic step. So it's natural to solve equations, and you can use hand to solve equations in an easier way. So if we turn the inequality to those equations, there are some typical ways we can solve. Right, so we want to write in those standard format, the x matrix multiplied by x equals to the vector b. But how do we do that? So that's a kind of a guide to give you how do we convert all the inequalities to equalities. And then to convert all the non-positive variable to non-negative. Because we always write those non-positive or non-negative way with smaller equal than 0 or larger than and equal than 0. So we always convert those to the non-negative, because the algorithm will search in this way directly. And last one is to convert unrestricted variables to non-negative variables. So it means all the variables will be non-negative. Not only to turn the sign from non-positive to non-negative, but also for those unconstrained variables, you also need to turn that to non-negative. So this is a computable way to turn the LP to standard format. So we are able to solve it facing any optimization, any objective. We have a set of equation, equality constraints, and all variables, all the x are non-negative. So if we write expanded way, it can be max or min. So this is just not max min, this is just max or min. So it's one objective. You define it. You have x as your decision variable. You have your c, which are the constants here as a coefficients in the objective function. And then you have your constraint coefficients, like all the elements in A, because it will correspond to how many x decision variables you have and how many constraints you have. So you have each element in Ij in the whole A matrix. Also you have your right-hand side constant terms of non-constraint. So the B are the constraints. So we define, if we have m constraints and n decision variables, we can write the problem in this way. This is the standard format. We will show the usefulness of the standard format. But before we show that, let's practice how we turn any problem to the standard format. It's kind of straightforward. When you obtain any optimization problem, you see, I just give you a formulation. It can represent any real problem you have. So you can write the problem in objective and constraints. So if you got the problem like this, we have original problem like this. We want to maximize objective function z. So it's a linear combination of the three decision variables, x1, x2, x3. Well, I have two inequality constraints and one equality constraint, and then they have two bounded variables. Okay, so if I got a form like this, how do I turn that to standard format? So the first one, here is just one addition to, because I want my right-hand side to always be non-negative variables, non-negative values as well. So I first easy way is multiply negative sign on both sides to turn it to a positive value. So it's just easy. First one is multiply minus 1. And second step is a bit not that straightforward, because I want to turn all the variables to be constraint variables and all the variables to be non-negative variables. But here x1 and x2, I know they are non-negative. How about x3? It is not constraint. Right, so here the x can be any of your problem decisions, like how much component you have in a mixing solvent, how many calories you intake for a daily meal, those values. So in the real problem formulation. But when we write it in a linear programming, when we want to solve it analytically or solving in the standard format using the algorithms, we want to turn to standard one. Because x3 is not constrained, I want to constrain it. So I cannot force it to be non-negative because it's not by its nature. I have to define additional variables to represent x3. And how to define that? Therefore, I use two new variables. I cannot just say x3 equals x4. It's no nonsense. I have to introduce another two and use the difference between these two new variables to be the new representative of x3. Because all the three, x3, s1, and s2, they're all changing. They can all be varying as a decision variables. So you don't really limit x3. You just use another two varying variables to define x3. right? But you can use these two to define any number. If you introduce another two variables, you can define any number by those two by using the difference among them. But you can define x1 is always larger or you can define both of x1 and x3 as non-negative variables. Therefore, these two non-negative variables can represent any of the original variable of x3. So this is a new way we introduce two more variables. It seems like we make the problem more complex, but because we turned to standard format, it's much easier to solve later. Then we have at this initial inequality or unbounded variable. Right, so examining up here, how did we bring? So we know initially here is x3, so now it's s1 minus s2. We know it's x3, so it's easier to return that. And here is x3 as well. And in the end, we have all the variables to be non-negative. So we no longer have x3, so it just introduced two new variables to represent x3. But these two new variables are non-negative. So these are a lot of these kind of the tricks when you formulate modeling. That's the beauty of modeling. You can always define new variables to represent the old ones and do some transformation. So this is one commonly used way to turn that to non-negative variables. Right? And then we continue, because we know in initial LP standard form, all the inequalities need to be changed to equality constraints. So we like to see the equal set. But we cannot force them to be equal. Therefore, we have to bring in some new variable called slack or surplus variables. So you can see their meaning by their name. If we say a slack variable, what does that mean? So if we compare with the previous one, we already have the objective function to be x1 minus 2x2 plus this is x3, right? 3x3. So now it's 3s1 minus 3s2. So it's the same objective function, but we want to change the inequality. So now we have the first one is smaller or equal, second one is larger or equal, third one is equality, so we don't have to change that. But to transform the first one, we hope to bring the sum to equal sum. But it appears to be smaller or equal, so we need to add another variable, s3 here. Right, so it's kind of difference variable. So here we call it slack variable because it is non-negative. So we plus this s3 to the first left-hand side, and then to make it an equal set. So this is a slack variable, and then we got the first one to be equality, but the second one is still inequality. Can we use the same strategy? Right, still the same, but now the sign is different because it's larger or equal than 2. So if I want to make it 2, I need to minus some non-negative value. Right, so here I need to minus s4, still all the variables are non-negative. I make this larger left-hand side minus s4 to make it equal. Right, so here we got the surplus, because it's very larger or equal, we got the surplus here. Therefore, all the variables we defined are still non-negative. So this is the standard transformation. By now, it looks like the way we desire it to be. Right, so we can then see the overall process. We want to maximize this z equals 1 minus 2x2 plus 3s1 minus 3s2 subject to the three equations. Well, my x1, x2 are the original variables. They're non-negative, it's good. And then I introduce s1 and s2 because I want to represent s3. I introduce x3, so these two combined to represent x3 initially. Well, the s3 is what? Slack or surplus. Slack variable because it's turned the original inequality to the equalities. So when it's smaller or equal, we add something to become a slack. When it's larger, we subtract something, so it's a surplus. Right, so we got the first two transformed using the second two transformed using the new variables S3 and S4, and then all my 6 variables are non-negative. So this is the way I turn that to standard format defined earlier. Right, so you can get a way to understand this further because we write it in a matrix form. So in a computer, in MATLAB, those kind of matrix vector form, it is preferred you write all the coefficients in a over row matrix A here. So if we want to write maximization, so we write my objective function Z, and I know all the 6 variables are written here. And C is a coefficient in the objective function. So what's the dimension of C? The dimension is a common problem you need to get familiar with, because in many of the matrix operation, you always got some error set because you put the dimensions wrong. So sometimes just take some transpose or turn that to another dimension, you got correct. But just when you program, think it in your mind what the dimension should be, because the C is written. We write in the C transpose, but when you impose, it's like a line vector to indicate the coefficient before all the unknown variables. You write the unknown decision variables as a column vector. So it's 6 rows by 1 column as a column vector, and the coefficient as a line vector, 1 row and 6 columns. So these 2 vectors will make my objective function. And then the dimension of A will then be decided by how many constraints you have in this row. So I have 3 constraints. I have 3 rows. And for each row, because I have 6 decision variables now from X and S, so I have 6 space, 6 columns for each row. So that is how big my matrix A will become. It's a 3 by 6 matrix to be a coefficient matrix. And because it's now the equal sign, it's convenient to copy the right-hand side to be the positive values, 7 to 5, because I already turned it all to non-negative values. Okay, so then this is the standard format. All the decision variables are non-negative. All right, so this makes it following algorithm much easier to solve. So that seems like a tedious work at the beginning, but if you want to program some algorithm, it's a good way. Makes the computer like this kind of representative. Okay? So you can try to get familiar with the standard format. Just take a minute to write down it yourself as a practice. It's a simple one. Minimization. Minimize minus x1 minus x2. All right. So first of all, how many decision variables you have now? Right, now you have originally it's x1, x2, and then during the transform, let's do it step by step. What's the first step? Okay, minimization. All right, and then first constraint, because it's no equality, so I can directly check. Okay, the first constraint is minus x1 plus x2 larger or equal to 0. Okay, so because it's larger, so I need to get first one. It's called a surplus or slack. So you should minus this surplus variable first, because all the variables are non-negative. But the second constraint, it only gives you the upper bound of the first x1 variable. So you think you don't have to deal with that because it just tells you the upper bound. Or we have to turn this to an equation as well. So I think you have made the choice, you turn that, because it's also an inequality. Only the 0 is defined as allowable inequality here. It must be larger or equal to 0 is possible, but for the other number is 2, is 3, I don't want to see those inequality in a standard format. It's still, you need to turn that to a equality constraint. Right, so you can, because it's smaller or equal than 2, you can then write a slack variable S2 to make it an equality. Similar for x2, smaller or equal than 3, write it to, so it's not 0, right? You should, the right hand side, don't change it. And oh my, is this correct? This seems my transform to a standard format. Right, and then I can write my matrix for C transpose A and B, because I got my standard format. I can directly copy the coefficient here. Right. Note that imagine when you have no variable here, you need to put the 0, because you will multiply this A matrix with X. So it's always 3 by 5, 4 by, there's always this square matrix format. Depending on how many constraints you have corresponding rows, and how many variables you have corresponding columns. So this is a way we turn the problem to the standard format. And this is the basis for the simplex method. For this algorithm, we need to turn the standard format and further conduct the simplex. Because simplex method is like a basic calculation we practiced last time as a row elimination. It's basically use the row operation to calculate and then find the next operation and then solve for the final optimal solution. So in this class, we won't teach you through all the details of simplex, but this is important you know the standard format as a foundation to this simplex algorithm. Why computer is able to fastly process it. This is a standard format for a simplex methods. Okay. But we give you some important definition here. We define a feasible solution as a non-negative vector x here that's satisfying ax equals b. So this is a definition for corresponding to the LP standard format, because ax equals b is your constraint space. It incorporates all the s variables as well. But if your solution satisfies this set of ax equals b constraints, it will be a feasible solution. And then the feasible region, we can then define it as a whole space made from the feasible solutions. Right? Because for equations, it's good you can draw the line clearly. Now if we only have 2D space, you can draw x1, x2, draw their correlations on this 2D figure. And then those constraints define the boundary of those conditions. If you look at the original problem, it gives you x1 and x2 to be the 3 constraints and define this region. So that region made by the feasible solutions we defined as a feasible region, denoted by S. So it's a set of all the feasible solutions. And then our goal is to find the vector x0 to be feasible, such that its value of the objective function is larger than that of any other feasible solutions in the case of a maximization problem. So if its minimization is always smaller than any other solution. So this is mathematical definition to be very precise. Right? It should be larger than any other feasible solutions. So if you want to prove this, you can always go back to the original definition to prove it. But it's always difficult. It's more difficult when we prove any. When you say the word any, it means you can never name all the possibilities and then prove it. You have to find some ways to prove. But this is original definition. When we search, we also try to search until it won't increase the value or until you think it is a maximum value. You terminate there. But by definition, it means this x optimal belongs to the feasible site S, and this objective value C transpose x0 is larger or equal to any of the other feasible solutions in the feasible site S. So this is definition. And then the optimal value of this linear programming will be the value for the objective function corresponding to the optimal solution, because the optimal value will be your objective function value. So it's your total profits, it will be your total, maximize your total revenue. So those will be the Z of your objective function. Okay, so this is the definition for simplex methods. Although we won't touch it, you can check the in book chapter. In our book PDF, it has a whole chapter. I'll show you later. Introduce the methods. If you want to read, you can, but it's not covered in what I teach or what I advertise in quiz. It's not required. I taught this last year, but almost using 1 hour. But students all complain, say it's none of use. So I only encourage, if you really want to understand the details, you go check there. I also checked. It's very tedious. It's not difficult at all, but it has a lot of steps. That's how you see. It is very classic optimization algorithm. So any optimization class, we try to teach this because it's so classic. Everyone knows the name. But it's really very tedious, like 7 steps. Each step you need to clearly add this row to another row, bring another variable and delete the other one. And there's a lot of criteria. But this is a mathematics algorithm. It's really not that simple as physics. You just use one equation, E equals mc squared. This one simple equation to indicate it. It's like algorithm development. You got a series of logics to search for optimal solution. But it's beautiful as well. You can, if you're interested, you can go there to see the details. Also, some very good videos on YouTube. It's normally 1 hour. If you want to see the whole process, you can follow the professor there to check the details. I just give you the overall philosophy. It's because we got the standard format of simplex method of LT already, right? So it's all equations. So we can apply this elimination scheme. So what's called Jordan elimination is just to add one row to another row and then calculate and reduce variables until you find the desired value for the variables. So it's reduce the system of m equations and n unknown variables to the canonical, or do still remember those concepts. So those row echo form, like you try to get it to reduce a variable, so kind of the echo form. Initially you have a lot, but in the last one it only gives you the equation, the value of the certain x variables. So this is like how you do the matrix operation until you get the final results to solve for the variable. Because it's equations, so it's solvable. That's why we need there the standard form to turn that to equations. It's basically to multiply any equation in the system by a positive or negative number, because each one is an equation. So you can multiply any number on both sides, it's still equation holds, right? So it's multiply them and add to any equation a constant multiply of any other equation. Once you got this equation, you can add that to a second equation. By this operation, you will be able to eliminate most variables in the system and get the final solution. So, but there are some conditions we got infeasible. So I think you check some problems when you have a very simple problem and too many constraints, you won't get a feasible solution. That can be explained by the standard format, right? If you have more variables than equations, and consequently the problem has infinite number of feasible solutions. So this is not bad because we have a lot infeasible. It means your problem is too relaxed. You have only if you have millions of variables to be decided. Well, just put very sparse equations there, very few constraints. Of course, you got a lot of results, but are they optimal? So you will see because it's a lot of feasible solutions based on your problem definition. But still, it's optimal if you choose one, but it's just a lot of feasible solutions. If you have few variables, have more variables and few variables and more equations, you might get infeasible solutions. Right, so this is a solving process. We don't touch the details here, but we want to use some examples. So we discussed those examples last class, just remind what we studied before, a typical problem for resource allocation. So here we have, if we have two products, so if we can produce X1 and X2 respectively for two products. And if I know the unit price is 2 and 1, so I know my or my unit profit is 2 and 1, I know my daily profit. And I put some constraints because the machine will have constraints on their machine operation time. So this problem we formulated last time already. I just won't go through the details, and we got some constraints here because it's a machine time, non-negative. Okay. So it's formulated as we want to maximize the profit constrained by the machine time and tuning time. So how do I solve this? So in a project, we don't need you to give analytic solution. You just go to software to solve for numeric. It's good if you can get analytic, but it also means your problem may be too simple. So we won't like you to math offer analytic, but it's good if you do some mathematical operation to show your thinking process. It's also very important, but it's not required. But for this simple example, we want you to understand how we can formulate the problem, how the computer helps us to solve it. It's also the solving process. Right, so this left-hand side is the original problem. So we have the objective function, we have the constraints, and we can then realize all the constraints. You can, because it's just x1, x2, so it's simple. You can plot all the feasible region and then get the optimal value. Because you evaluate your objective function, so this z is 2x1 plus x2 is like 3D space. You have this z calculated at each x1 and x2 on the figure, while your x1 and 2 are constrained by the three constraints and non-negative values. Okay. And you are able to get optimal value. This is a direct realization. But I want to show you if we change the problem formulation, what if I consider I have three products. So it's not to do a mass transform, I change to another problem statement. If I have my third product, x3, then I got a different problem. I want the profit from x3 is also 1, similar as x2. But then I have more constraints to my problem because x3 will also use a machine time A, will also need tuning time. So this is a new problem formulation. Then it won't be that easier to realize because for 3x it's a maximum dimension we can realize properly in a human understandable way. When it's higher dimension, you have to use more complex realization, or when it's beyond 5 or 6, it's even not possible to realize it. But for 3, you can still see I have x1, x2, x3, and then draw all the constraints there, and then calculate the z value to find the optimal solution. That's still possible because it's all linear constraints, so it's a convex set. Correspond to what we learned initially. So linear programming is a special case of convex programming. So we are able to find the optimal solutions through a search. So this is an example. We just show you the realization, how we can draw the constraints and search. But later on, let's move to the this class to this slide, another set of slides to see how the detailed search process is like. Okay, so we briefly introduced the software last class already. So most of you use MATLAB, GAMS, Python for the programming, but it's either specifically designed for LT, more for commercial use. It can be easily used. And you can use a linear programming toolbox in MATLAB to use some algorithm, and also in GAMS. We'll spend some time later to cover this content in more details. But I want to move to another set of slides. Right, so this slide is mainly for this week. We got a general understanding of linear programming, and then we can touch more into the fundamental problem formulation, the examples, and also the algorithms of it. So it will be very interesting to see some of the new concepts you won't see in other problem formulation. It's very interesting laws defined as well. Okay, so still I put some recap here because I think this kind of example is very useful for your design project as well if you're a Chem Eng student. So you got a lot from your Aspen HYSYS simulation, but when you want to optimize something, you didn't have a clue where to start. So this kind of optimization framework is really you don't directly optimize on your design simulation. You can use the input and the output. Like if you found a column there, you know this is like certain product feedstock input and a certain product output. Then you can take those values out. Those values can be your parameter in your optimization, and then you define some of the objective to be economic or environment and use that to solve. That's a very straightforward way. You can add more value to your design as well because it kind of optimize the design solution. It's also very common in your daily work. If you work as an engineer in oil and gas plant, you can optimize the operation process as well. So this kind of problem, if you write in the GAMS code, the same problem I showed before to connected CSTR, it has many good examples here. I write the code here because I see many of you when you write the GAMS code, because I fully understand when I first started to use that, it's very weird to me because I seldom use this right in Hybrid. It's just like I write every line to define everything. But actually it has very good function. You don't have to write each equation to define each parameter. You can probably use something like use set. If you define the chemicals, like in your design, if you have 10 chemicals, you don't want to write 1, 2, 3 until 10 every time. So you can use the set of the like define I to represent all the chemicals in your problem. Then when you write the constraint, you can just write the constraint with respect to I. You don't have to write it with respect to all the every time copy the index. So if you try to simplify your coding, at the beginning your goal is just to make it runnable, configurable, give you a solution good enough. But later on, when you want to solve larger scale problem or you really want to use it, try to think about how to make your code easier for configuration and more beautiful for reading or more efficient. So that's a lot of these things. It's also programming Hybrid. You can use a lot of these representative symbols to indicate. And if you're not familiar with those, you can load some examples from the library. Like for GAMS, they have very good examples. Those are very good reference for you to initially practice writing. Even in Python, you try to learn from some manual code to get a good habit from the examples, how they write the good code, and then follow that. You can start with the formulated code and do some yourself configuration. That's sometimes more efficient because your key contribution is your own understanding. That in that sense, you are more like an architect, not really the programmer. You are the designer to master that problem. So that's a proper way in the end to use this optimization code properly. All right. And then because this week we are supposed to release you the group project, but we extend the individual project a bit. So by the weekend, we will give you some topics on the group project. So we did a brief survey. So only one group would like to do some self-configured project. I still keep that option open if you really have a strong interest to propose your own problem at the same or even higher difficulty level. You can get my free to go signal if you discuss with me. But if not, I will give you the very general framework as well and provide you some preliminary statement and some initial data so you can start with. So it's very broad. We call it smart city, smart urban system, or here in Singapore, smart nation we are building. So smart urban systems focusing on the energy, water, food, waste nexus. That was covered by some of the guest lecture. This about how they can turn waste to energy, turn waste to the useful resources, or use waste to generate energy, and also how energy system. Because now we are developing kind of the sustainable country, also the food strategy, if you have seen the news, Singapore used to have little food industry. All the food is imported from Malaysia. So even you see some made in Singapore, they may just be imported from other countries and just labeled in Singapore. So it's made in Singapore in most cases. But from this year, the government released, if you care about the budget, they released a huge focus on the food self-sufficiency or sustainability. So that's about the vertical farming, urban farming. Those topics are feasible as well. So this broad project, I will give you at least 4 or 5 possibilities you can go to pursue. It's optimization problem. You want to optimize something, but you don't have to. Each group can choose your own interested directions. So later I'll give you overall statements, and each group can pick 1 or 2 topic. Or if you want to do an overall urban design, that's also possible. If you want to do a design of a farming system, indoor farming, vertical farming, that's possible. If you want to do a design of an energy generation system, or you want to design for the home energy management. That's all allowable topics within this framework. Okay, so we'll give you the topic later on. I hope you have found your groups if you desire to. So by tonight, I will randomly assign the rest if you have not signed up for a group. So today is the last chance. Just find your group members if you want. You know, from this year, the university forced the classes. We no longer have the right to allow you to choose your team because they say in future working environment, you don't have the right to choose your colleagues. So we should practice this from college. So from now on, the university assigned the new system, the Lumi NUS, right? We haven't used that for this class, luckily. But in that system, no one has the right to choose your teammates. You have to be forced to randomly choose a team. So cherish the opportunity to choose a team member. I bear the burden. Otherwise, if the boss side, I cannot do this for you, today is the last day to form the group. You find your colleagues. I think it's also an interesting thing. You can find your good friends to work together because you're familiar with each other. But sometimes you really got new inspiration when you form a team with some people you don't know. Right? So it's really a good opportunity to find a good colleague. But it's very reasonable to find a good team to work together with people you haven't worked together before. All right. So let's start with these groups. So better we have 5 to 6. Better not leave 4 people because it's a bit unfair if we only have 4. So the workload will be too heavy. So preferable 5 or 6. Okay. And would you like to have a final presentation? That's also my question here. Because last year we think the final presentation is very effective. But I think most of you will not fully complete the project by the last week. So I will extend the deadline to the reading week. So after reading week, each group submit the final report. But the last week, last year we had the presentations by each group. It was quite good, or informative presentation. After the presentation, you can further revise based on your understanding of the problem, the other group's insights, and the feedback from lecture. So probably you can let me know how many of you don't like to have a presentation. No presentation, right? Okay, I know you don't want to raise your hand. Our presentation, yes, presentation. No one. Okay, let's see. But if no presentation, what do you think is a fair way to grade the project? I open the discussion because it's always difficult for those projects to be graded. Peer evaluation, that's too tough. That's optimization. That's a game theoretical model. You do peer evaluation of each other. All right, so I think it's better we still do some kind of presentation, but let's discuss later. All right, so I put more brief description here. So in the end, we will deliver the report with the most important thing. Presentation used to take like 20%. It's good practice, but let's see. So the final deliverable will be the report that describes your approach, results, and conclusions. So it's still like 8 pages. Now, not a huge report you give, but also incorporating the summary, background, methodology, results, analysis, conclusion. So I now plan to schedule group presentation in the last week. If you have very strong opposing opinion, you let me know what is the best alternative to presentation. I can consider it seriously. Right. And also another thing is, last year some group did very good job and we write a paper and it's published with all the students' name on it. So it's a very good way to showcase your work from a class. You publish some, it's just a 6-page paper, but it's very nice practice. You have your team members as a good memory, publish a paper with all your team members' name there. So that's also a good option. I can help you to formulate that in a paper format, and then that can give you bonus in the end as well. I will add a bonus to like a publication criteria here. So consider that option as well if you want to do something. All right. So the details the rubrics will also be released together with a statement. Okay, then let's continue with the slides. I think we don't have to go through all the definition because we reviewed already. But again, for LP, remember it's only continuous variable. It's only a single linear objective function, linear equality or inequality constraints with those formats. And for this initial problem formulation, we introduced it during the World War II. So at that time, it's about military logistics. The most famous one is called the Berlin blockade and the airlift. So here I put the details here. If you want to formulate this, as some of you may use this as individual project already. So it's very nice logistic programming. In the airplane operation, it's a huge department for the operation problem. And even nowadays in oil and gas, they have a lot of people who take care of the operation module, operation unit, do a lot of work. So in this case, if they have the airplanes, flights, and the food and supplies to be delivered, and they have some constraints like time and logistic requirements. So this is really when you see this huge problem, you cannot really just do some planning by just thinking about some numbers. So this genius Danzig solved this Berlin airlift linear programming, so which is regarded as one of the very beginning of LP, by hand using the simplex method. Because no computing results at that time, they're also even during the block, so they solve this by hand, just like the way we solve this. They solve the huge problem by hand using the simplex method. That's why we should say the simplex method is handy, because if you turn that all to constraints, then you are able to solve it. It might take days, but still it's solvable. Right, so this is the first LP problem. And then when I move to our that's more domain relevant, think about the operations planning. We showed you some very basic example in the last lecture. If we want to feed some raw materials and get certain products for my production unit, how do I plan? Right, so we have the feed requirements for each product. If I have 2 feed and the 3 products, I have provide you in the company, normally those are from the historical market trend or from the supplier's price. It's relevant to your supply chain management as well. So you got your supplier's price and they give you a range of the product, and then you got the problem that can be formulated as linear programming. Right? You can probably write it. If I ask a question, how much of feed 1, the feed 2 should we use? Then you can write the program like using the revenue. You want to maximize the profit, right? Revenue minus cost. You use the total selling money minus how you spend the cost. Could be the profit as an objective. Well, you got the constraint here. Because the constraints are like the mass balance, so you got the product linking to the feedstock. But in the real problem, it may not be this easy. You have allowed the feedstock and product, but still it's equation. If you can write it in the equality, it's handy, it's easy to solve in the end. Now by hand, it's not easy. By computer, it's very fast. And then you have your constraints lower upper bound for this. Right, so we discussed if we have such simple model, when we use that in real world, what further improvements can I make to the model? So we got some interesting numbers to say we have a lot of graduates, undergraduate students, when they graduate, you go to ExxonMobil to work. So it's like a lot of students go to ExxonMobil or the other companies. And the salary got quite high, right? Last year, we just discussed the survey. So ChemEng students got very high salary compared to the other engineering major. Just a bit lower than business, but almost the highest in engineering in a sense. So it's quite good, but a lot of the oil and gas or ChemEng companies, now they would like you to have some management skills, or they want you to operate the plant, to plan the production. How do you do that? What factors will you consider in such scenarios? Right, so it's like operations planning, and the major issue to help the decision maker to decide is what to do, which means what to produce, what to buy, when and where to do it. So here we formulate a problem like what to do. We know what to produce for P, what to use for the feedstock, but when and where to do it is also very important. When we formulate many problems, we consider time step there, we consider the spatial there. So in the large-scale research questions, we always have we want to do different time scales, from the yearly operation to kind of a monthly production plan, daily operation, and then even down to more real time. For energy industry, for example, electricity, they have the yearly overall goal. They have a 10-year development plan or 5-year plan, and then they have a yearly overall objective. Then they have a day-ahead market. You can budget for next day operation. Then you move to real time. You may have 15-minute market. You can then have a real-time market. So it's a lot of those time-dependent operation, because the price, the suppliers, if your electricity suppliers are this real-time varying price, then as a plant operation, company operator, you will consider those that will influence your decision. So these economic decisions will be decided by when and where to do it. We sometimes rely on the map layer now. The visualization is a powerful tool. We're able to use the geographic information to describe the whole system or the layout of the system to plan where to do it. Right, so before we simplify it, but you can get more chance to formulate such problem for your study. This will also be useful for your group project, because we'll consider the urban systems. It will have a lot of spatial and temporal scales. What is that? Should be okay, huh? not be optimized. So you will then need to have some of the decision variables, depending on the time. So here you will have the time as an index. You will put the t there in your consideration, and then this will be considered in each of the each of the period. So decisions will be made in this successive time period. What does this mean? So it means your current time is never independent. It's always depend on your previous time's decisions. So the time flows, but you always get the current time or next time. The starting level for the next time will be related to the previous time starting level plus what you did in the t time. So you have this kind of accumulated amount. I think there's some class, the system dynamics. It's a whole philosophy for the system dynamics. What you do in the certain time is not independent. It's related to what you did previously. It's dependent. It will influence what you will do next. So it's like the time slice here. So when you formulate the problem, you can consider to add the time figure. You can do a snapshot where you capture the whole thing in 1 year operation and do overall. But if you want to be more, make the problem more interesting, you can consider the time-dependent operation, especially like the supply chain problem or some of the operation problem. It's very important to consider how your, like the supply chain we studied earlier, you have your two feed, right? You have to consider the two feed to the final product. But if you extend that to the whole supply chain, you know this product is not directly manufactured from the two feed. You have to consider how these feed are transported to the final supply and how much time they took in between. Storage, when it needs to take some rest to do some storage, and then in the factory plant or warehouse plant, transportation. So it all link in from the input to output. It's a lot of intermediate steps. Some good examples are available in GAMS already. So that's GAMS. Actually, the samples are very good. You can directly check some examples in GAMS and learn how they formulate those problems. All right. So after the overview again about examples, we kind of move back to what we stopped to the algorithm, because I know algorithm is not that exciting, but still it's important. You know how computer solves this for you, so we still have to learn something about the algorithm. The basic one we introduced about the tool for linear programming, interior point and simplex. But before we go to algorithm, we know for good feature for linear programming is that a local optimum for linear programming is global optimum. So it will search for it. It always gets to reach the global optimum point. That's also why we sometimes like to formulate a problem in a linear way. Although you have to make some assumptions in the formulation, or you have to do some linearization by mathematical operation for a problem. But in the solving process, it's very good to give you the global optimal solution. Okay. And for the numeric optimization, because the algorithms are always based on the numeric approach, it's not like the analytic we can solve for it. So for numeric one, it's the basic idea is to use the local information first in this iterative scheme, determine the feasible next point that can improve the function, to find a way to climb the hill, and check if the further improve is possible, to check if you are going uphill, if the way is correct. And if yes, we continue to go. If no, we stop and research a way. So that's a very basic idea, how we search for optimum point. Okay. And then we practiced just now how we turn the normal problem to a standard format, as we just have on the board. We were able to write it in the standard format, and then the simplex search. So this one we introduce you the philosophy, but again, for the overall framework, how do we define it? It's again like we initialize the problem at the initial iteration, choose a feasible starting point. So you should always choose a feasible starting point, because at the beginning you are able to tell if your x0 is feasible or not. Don't waste your energy to start from a very far away point. It's always to start, when you give the x0, some algorithm asks you to input x0, try to guess a reasonable one that is closer to your optimal point. If you are lucky to guess the right optimal point, then just within no time to give the solution. But try to choose one feasible starting point, and then the simplex direction will be true. So this is the way we introduce how do you decide the simplex direction. That is a mathematical operation there. We won't touch the details. And then we choose the step size. It's always say we will climb the hill, we need to decide how far away we go. When we are far away from the optimal point, we can choose a larger step. When we feel it's closer, can reduce it. But it's all like flexible thing based on the algorithm you choose. Right? So when you have those simplex method, it defines the step size in such a way that it chooses the direction to go. So this is a defined way in the simplex algorithm. We don't give you the details here. You don't have to understand the full details. Just to know it, choose the step size, and then update the next solution and calculate this value. So the complex part is how do you choose the direction, and how do you decide how big step size you go along that way. So here, simplex method gives you some standard like golden rules to choose its two values. Okay. So we can continue. So I think we almost touched the examples already, just resource allocation, right? So we already used last lecture to give you a sense of this already. We don't have to repeat. So this is a new concept we will introduce for LP. It's called do. So this is a very interesting, very magic word in the linear programming. Because we studied the standard format, we learned optimization, and how do we solve that? Although we know simplex is able to solve that, when the problem is very complex, simplex is not quite efficient to solve that, and you might do some different operation to solve the problem. And this symmetric dual linear programming is a very powerful term. This is quite unique term we hear in the mathematic term we use in optimization. So it's defined in this way. We all know we have a prime problem, it's called primal. If we want to maximize some objective function, and it will have a certain constraints we can write in the matrix format. And then we define the dual problem in this way. Initially, you might feel it quite weird, but the dual problem has very nice features, mathematic features, to make it useful. So this word is interesting. I see some mathematicians say this word is quite magic, because in Chinese, you know how to translate this word. I know many of you don't speak Chinese, but in Chinese, this word exactly has a similar pronunciation with the English word. It's called, you can have a guess, or if you know it already. Good way to learn. Even not in Chinese, I think little in French. In French, it's also similar pronunciation of this. And it has very nice meaning. Okay, I can leave it for your own search later. But this has a nice feature. How do we turn a primal to a problem to a dual problem? It's based on this correspondence formulation. Right, so initially we have your Z, and then you want to turn the maximization to a minimization, and to another set of the variables, decision variables Y, but your initial constraint B, those are constant, right? We studied B will become your coefficient in the objective function. So now it's minimization YB. The B is the same value here. And because you you turn the dimension, so the A will be written on the right to Y. So YA, well, initially it's smaller or equal, then it's defined in blue as a larger or equal. So now you change the position of B and C. It becomes the C as the initial coefficient, and now it's in the constraint. And also all the variables are non-negative. So this is a way to change the problem from a primal to a dual problem. So we will introduce why we want to do this later, but you can try to get familiar with this format first. All right, let's take a 10-minute break. Maybe let's come back in 17 to continue from here.